Solo due note per introdurre Hugh Jenkyns, e lo farò in italiano, spero che tutti mi possiate seguire. Jenkyns è professore emerito di sedimentologia nell'Università di Oxford e ha contribuito con le sue ricerche al progresso della geologia in vari settori e in particolare al riconoscimento alla scala planetaria di alcuni eventi anostici nelle successioni sedimentarie pelagiche mesozoiche, eventi correlabili nel tempo con i cambiamenti climatici globali succedutisi sulla Terra. Le sue prime pubblicazioni alla fine degli anni 60 trovano supporto nelle ricerche condotte nella Sicilia occidentale per la sua tesi di dottorato. L'analisi tettono-sedimentaria della successione mesozoica siciliana, oggi tettonicamente inglobata nella catena siciliana, ricostruisce per la prima volta la fisiografia di un segmento del margine continentale della Tetide, l'ormai scomparso oceano che separava l'Europa settentrionale dall'Africa durante il Mesozoico. Partendo da questi risultati, Hugh ha successivamente esteso all'Appennino, alle Alpi meridionali e aree circostanti, Spagna, Croazia, Grecia, questo rivoluzionario approccio per evidenziare il segnale paleotettonico, paleooceanografico e paleoclimatico dei sedimenti pelagici. Queste varie conoscenze gli hanno permesso di interpretare e collegare le ricostruzioni della regione tetidea agli analoghi ambienti attuali degli oceani Atlantico e Pacifico, da lui studiati nel corso delle campagne oceanografiche del Deep Sea Drilling Project, prestigioso programma internazionale per la conoscenza dei fondi oceanici. Hugh Jenkyns è uno studioso con conoscenze profonde del pensiero geologico, come pochi altri che lavorano in questo campo. Creatività ed originalità della ricerca si riflettono nella capacità di conoscere come importanti i problemi geologici al loro nascere. La sua statura di scienziato, che traspare dalla produzione estesa e di impatto elevato, più di 160 lavori su riviste prestigiose, è confermata tra l'altro da numerosi riconoscimenti internazionali. Altrettanto intensa appare il suo impegno di insegnamento in patria e all'estero e in particolare in varie università italiane, dove ha trascorso alcuni anni sabbatici in stretta collaborazione scientifica con colleghi italiani, come risulta dalle significative pubblicazioni in comune. Si può ben dire che Jenkyns è divenuto uno dei più profondi conoscitori della geologia italiana. In conclusione, i risultati raggiunti qualificano il professor Jenkyns tra i più autorevoli geologi europei e lo rendono perciò pienamente meritevole di essere accolto come socio straniero nella nostra Accademia, che ha visto e vede tra i suoi soci stranieri alcuni insigni maestri e scienziati internazionali come L. Fisher, Albert Balli e tra i più giovani Daniel Bernoulli. Sicuri che Hugh Jenkyns bene e presto si inserirà nel contesto culturale dell'Accademia dei Lincei, portando contributi importanti e originali, gli diamo il più caldo benvenuto. Grazie.
It's a great pleasure and a great honor to be here. I too will be talking about time, but I deal with geological time, and 1,000,000 years is just a click of the fingers. So there's a change of scale. Geologists believe that the Earth's climate has changed a number of times from a so-called icehouse state with ice at the poles, the conditions we live in today, to times when there was no ice at the poles and the climate was warm. What is the evidence for that? You can see the distribution of these so-called polar dinosaurs, but the evidence is ambiguous because we don't know whether they were cold-blooded or warm-blooded, and so what they tell you about climate is perhaps not entirely clear. There's another interesting piece of evidence, moving from the animal to the plant kingdom, in this fossil here. It's a breadfruit tree leaf, and these are tropical floras which live today at temperatures of about 15 degrees centigrade minimum. And here it is being found in the Cretaceous sediments, the Mesozoic sediments of Greenland. So if we look at this little map here, this is how we think the world looked in the Cretaceous times. You can see where the breadfruit leaf was found. You can see where this so-called champsosaur was found, which is a reptile, so that's cold-blooded, so that tells you that the temperature was warm. So this is, if you like, qualitative evidence as to the prevalence of warm climates at high latitudes. If you want something quantitative, you have to do something a little bit different. And almost by accident, you can see there's a station here that was a research station that was on an ice cap in the Arctic, moving around in the pack ice. And they put down sediment cores, and they found one core that actually encountered Cretaceous sediments, black muds. And using a new paleothermometer, which actually came out of Utrecht, looking at lipids that come from archaea, they change their structures as the temperature changes with the number of cyclopentane rings. So we were able to actually come up with a temperature, and it seems to be somewhere between 15 and 19 degrees for perhaps of about an age of about 80 million years ago. So high latitude warmth seems to be real during these greenhouse phases. But within those warm phases, there are ultra-thermal, even warmer phases, which have now been identified. And that's done by looking at the chemistry of the rocks in question. And these sediments that were deposited during these ultra-thermal times, these hyperthermal times, within this general context of a greenhouse Earth, have some very interesting properties. And as Raimondo was telling you, I have tried to look at these across the Italian peninsula, ranging from Sicily to the Southern Alps. So a little bit of history. If we fall back in time to 1891, we have Guido Bonarelli, a count who was a geologist trained in Rome, and while he was a student, he made a map of the territory around Gubbio. As you can see, he has a wonderful moustache, I baffi sono magnifici, so that's his interesting characteristic. And the section he described probably looks like this. This is the natural outcrop of the Botticoni Gorge. Now well known, of course, for the Cretaceous-Tertiary boundary story and the death of the dinosaurs and so on and so forth. But if you look at that particular outcrop and walk down the road, you see there is this sort of darker area here where the sediments are totally different. So there's an interval here of sedimentary rock. It's about 1 meter thick. Below there are limestones, so they're made of calcium carbonate. Within that dark interval itself, that's one of these hyperthermals, it's about 94, 93 million years ago, there is no carbonate, and it does instead contain a lot of organic matter, planktonic organic matter, and the remains of plankton. And then you see it switches back to limestone again. So there's been a dramatic change in the nature of the sediment, which is suddenly not preserving calcium carbonate, but instead is preserving large amounts of organic matter, which are, of course, the source rocks for oil. So this is one of the characteristics, then, of these hyperthermal intervals. They're associated with the deposition and preservation of organic matter. So we can do a little tour. So we're jumping around to Tunisia. We're looking at the same interval of time, the so-called Bonarelli event, as it's sometimes known. Tunisia, eastern Sicily. That's the English version. It's only 10 centimeters thick. It's rather weak and feeble, really. And you find something similar if you core it in the Atlantic. And even if you drop into the southern hemisphere, you can find something else again that looks very, very similar. So we're dealing apparently with a global phenomenon when during this interval of time we did not preserve so much carbonate. That was depleted relatively, sometimes to zero, but we were instead depositing huge amounts of organic matter. And that's telling us something about changes in plankton productivity, the flux of organic matter to the seafloor, and it's also telling us something about the degree of oxygenation in ocean waters. So if we make a map of the distribution of these organic rich sediments around the globe, you can see there's a fairly impressive spread. We have very few locations from the Pacific, but that's because primarily we have a lack of cores that come from that particular area. So we have then oceans starved of oxygen during this interval of time. And these have become known also as oceanic anoxic events. So you can choose your nomenclature. You can call them hypothermals if you're interested primarily in the fact that they're so warm, or you can call them oceanic anoxic events if you think the changes in ocean redox are the factor of prime interest. And there are, of course, geochemical changes within the oceans and the atmosphere that go hand in hand with both these phenomena. So there we are, that's our interval of time, and not only then very high temperatures, deposition of organic matter, but also probably ocean acidification. We have to explain the lack of calcium carbonate in the Bonarelli level itself when you're depositing all that organic matter. So a whole chain of events here, interconnected phenomena, which are telling us something about a very unusual state of the oceans when we're dealing with this greenhouse state of the Earth. So that's character number one, Count Guido Bonarelli. Character number two, more tangentially perhaps, Raimondo Celli, used to be a professor in Bologna, and he gave, or has given his name to another level of organic rich sediment, which you can find very well exposed in the Marche Umbrian Apennines, behind the characteristic net that you see along many Italian roadsides. You see it cropping out at the base of that particular image there, and it's very like the Livello Bonarelli, but the sediments surround it make the contrast perhaps a little less obvious, as you don't have the sort of white and pink limestones that you see above and below the Bonarelli itself. But it's exactly the same thing, effectively, same phenomenon, the same types of sediment, but as you see, much older, coming in at about 119 to 120 million years ago. These are other examples. There's an example from Sicily in the top left, and two examples that have been caught from the Pacific, which you can see, one below and one in the right-hand side. So again, it has this global context, just like the Bonarelli level. And again, you find examples not only in and around Europe, but you find them in the Pacific as well. Another interval, stream warmth, and our oceans starved of oxygen. So we're making organic rich source rocks, which is obviously useful if you're in the petroleum industry. If particular intervals of time are source rock prone, then that perhaps helps you in understanding which sediments might actually yield oil. So there's our interval there, and this again would seem to be not only a hypothermal, not only an oceanic anoxic event, but also an interval of ocean acidification. So another character here, Giorgio del Piaz, you can see him with his field vehicle, and he made an interesting study in the sediments of the Venetian Alps. I have it written up there, and you can see it's written in Italian. È una fascia particolare che ha il suo massimo sviluppo nella regione extra-alpina, ma della quale, per quanto sporadici e limitati, non mancano esempi anche nel bacino mediterraneo. So that's an interesting insight, because it tells you that he already, with these particular sediments, and these are even older, they're about 183 million years old, he realized he was dealing with a regional phenomenon. If you prefer the language of Shakespeare to that of Dante, then we can switch it comme ça. So let's just look at other examples of that. This is one from Yorkshire, UK. Black shales, same age as those described from the Southern Alps. And this particular outcrop here, which really no longer exists. And here there's an interesting thread which ties us into the history of Italy. In fact, a rather tragic story of part of Italian history post-war. You'll see in the bottom right-hand corner there's a small amount of water. And if you were to stand where I stood when I took this photograph in about 1980, and were to turn your head to the right, you would see this. And I imagine that many of you recognize that. That, of course, is the Vajont Dam. And, of course, one of the reasons why that outcrop existed, and I was able to work on it, was because of this flood of water that ran down that gorge, crossed the valley and destroyed half the village of Longarone. So this is how the outcrop used to look. It's now entirely covered with trees and with bushes. So that's just a little vignette, a little bit of Italian history that shows how these sorts of factors can tie into the rocks that you can study and help you perhaps build a story. So again, I can make a map. There's one of the black shales, those described by Giorgio del Piaz, which have this global spread, and once again another interval, another hypothermal with our oceans starved of oxygen. So we have to ask, why did they happen? What caused them? And again, we can use the old geological maxim that the present is the key to the past. So just some sort of rapid images of the present day oceans. You can see where organic productivity is high. This is where there is lots of plankton in the oceans. It's the shelves and the marginal regions and the equator, particularly around the Pacific, where you have high organic productivity and a high flux of organic matter to the seafloor. The organic rich sediments themselves are primarily concentrated in the shelf and marginal regions, and the deoxygenated waters are again in the same regions to some extent and also extend out across the equator. And if you look at the pH of the ocean waters, you can see it's actually also most acidic in that equatorial region where the pH is lowest. So you can take those 3, 4 images and ratchet everything up, and that's the sort of picture that you have to come up with when you're imaging the greenhouse world and the time of these hypothermals. So the evidence suggests that high volumes of CO2, we think it came from volcanoes, warmed the planet, increased weathering on the continents and in the oceans, stimulating growth of plankton and a flux of organic matter to the seafloor, as well as acidifying the oceans. And during its transit through the water column, that organic matter would be oxidized, and that would lead to, obviously, an oxygen demand and a loss of oxygen in the oceans. So that, we believe, is the chain of events. And you can make these various cartoons and look at the chemical behavior of a whole series of ingredients, different chemical compounds, and imagine very extreme states where the oceans might actually become euxenic, and both oxygen and nitrate had been used up. Sulfate was your oxidant, and you were actually liberating free hydrogen sulfide in the water column, and you then get organisms like green sulfur bacteria, which can grow and leave a molecular trace in the sediment. So global warming, we believe, has caused these hypothermals, these oceanic anoxic events, these ocean acidifications. As I said before, we think this comes from massive volcanic activity, and there is obviously a coda to this if we're looking at what's happening today. Here's a very recent paper just published in Nature looking at oceanic heat content, actually very niftily by looking at the amount of oxygen and carbon dioxide in the atmosphere which is released as ocean warms. And you can see that the oceans are warming. And if you look at the decline in mid-depth dissolved oxygen over time, those are mostly Pacific records. You can see they're drifting down. And in fact, if you look at a much sort of smaller timescale over a few years or tens of years, you can see this progressive deoxygenation is taking place. So the phenomena that I've described from this greenhouse world are, if you like, a picture of the Earth in extremis, and there are processes going on at the present time which actually recall in many ways what went on in the deep geological past. So global warming, as I've said, hypothermals, oceanic anoxic events, oceanic acidification events, similar phenomena are happening today. So in this case, the past is perhaps the key to the future. And I leave you with our 3 characters.